Okay, I should try and get started. Okay, so what we're going to do today is we're going to try and do everything else that you need to know about word vectors and start to learn a teeny bit about neural nets. And then we'll kind of get much further into sort of doing more with the math of neural nets next week. So this is the general plan. So I'm going to sort of finish up from where I was last time with optimization basics, then look a little bit more about word-to-vec and word vectors, and then some of the variants of word-to-vec. And then I'm going to briefly consider alternatives, sort of like what can you get from just counting words in different ways. Then we're going to go on and talk a little bit about the evaluation of word vectors. The topic of word sensors that already came up a couple of times last time when people were asking questions. And then towards the end, start to introduce the idea of classification, doing neural classification, and what neural networks are about, which is something that we'll then expand on more in the second week. Before I get into that, just notes on course organization. So remember the first assignment is already out and it's due before class next Tuesday. So then our Python review session is going to be taught this Friday, 3:30 to 4:20. It's not going to be taught here. It's going to be taught in Gates B01, the Gates basement. And encourage everyone again to come to office hours and help sessions. They've already started. They're listed on the website. We're having these sort of office hour help sessions in classrooms with multiple TAs. So just turn up if you're on campus and you can be helped. And if you are on campus, we'd like you to just turn up, though we do also have a Zoom option for Stanford Online students. Finally, I have office hours, which I have not yet opened, but I will open sometime tonight. They're going to be on Monday afternoons. Now, obviously, given the number of people, not everyone can make it into my office hours, and I'm going to do these by appointment, so they're by 15-minute appointments on Calendly. But, you know, I'm very happy to talk to some people, and, you know, I put this little note at the end saying, don't hog the slots. Some people think it'd be a really good idea if they really work out how to sign up every week for an office hour session with me, and that's sort of a little bit antisocial. So think about that. Okay, so at the end of last time, I did a sort of bad job of trying to write on slides of working out the derivatives of word-to-vec. And hopefully you could read it much more clearly in the version that appears on the website, where I was doing it at home more carefully. So that was saying that we had this loss function and our job was to work out its derivatives, which would tell us which direction to go to walk downhill. And so I didn't really quite finish the loop here. So, you know, we have some cost function that we want to minimize, and then we work out the gradients of the gradient of that function to work out which direction is downhill. And then the simplest algorithm is then that we work out the direction downhill, we walk a little bit in that direction, and then we repeat. We work out the gradient at this point, we walk downhill a little bit, and we keep on going, and we'll get to the minimum. And with a sort of a one-dimensional function like this, it's sort of very simple. We're just walking downhill. But when we have a function of many, many dimensions, when we calculate the gradient at different points, we might be starting to walk in different directions. And so that's why we need to do calculus and have gradients. And so this gives us the basic algorithm of gradient descent. And so under the gradient descent algorithm, what we're doing is that we've got our loss function j, we're working out its gradient, and then we're taking a little multiplier of the gradient, so that alpha is our step size or learning rate. And that's normally alpha's a very small number, something like 10 to the minus 3 or 10 to the minus 4 or maybe even 10 to the minus 5. So we're taking a really little bit of the gradient and then we're subtracting it from our parameters to get new parameters. And as we do that, we will walk downhill. And the reason why we want to have a small learning rate is we don't want to walk too fast. So if from here we worked out the gradient and said it's in this direction and we just kept on walking, we sort of might end up way over here. Or if we had a really big step size, we might even end up at a worse point than we started with. So we want to take little steps to walk downhill. And so that's the very basic gradient descent algorithm. Now, the very basic gradient descent algorithm we never use. What we actually use is the next thing up, which is called stochastic gradient descent. So the problem is, for the basic gradient descent algorithm, we've worked out for an entire set of data what the objective function is and what the slope at the point of evaluation is. And in general, we've got a lot of data in which we're computing models. So simply trying to calculate our objective function over all of our data for our model, the training data for the model, would take us a very, very long time. And so that's very expensive to compute. And so we'd wait a very long time before we make even a single step of gradient update. So for neural nets, what you're always doing is using this variant that's called stochastic gradient descent. And so for stochastic gradient descent, what that means is we pick a very small subset of our data, like maybe we pick 16 or 32 data items, and we pretend that's all of our data, and we evaluate the function j based on that small subset and work out the gradient based on that small subset. So it's a noisy, inaccurate estimate of the gradient, and we use that to be the direction in which we walk. So that's normally referred to also as having mini batches or mini batch gradient descent. And in theory, working out the gradient based on this small subset is an approximation. But one of the interesting things in the way things have emerged in neural network land is it turns out that neural networks actually often work better when you throw some noise into the system, that having this noise in the system gives you jiggle and moves things around. And so actually, stochastic gradient descent not only is way, way, way faster, but actually works better as a system for optimization of neural networks. Okay, so if you remember from last time for word to vec, the idea was we started by just saying each word has a random vector representing it. So we will literally sort of just get random small numbers and fill up the vectors with those random small numbers. There's an important point there, which is you do have to initialize your vectors with random small numbers. If you just leave all the vectors as 0, then nothing works. And that's because if everything starts off the same, you get these sort of false symmetries, which means that you can't learn. So you always do want to be initializing your vectors with random numbers. And then we're going to go through each position in the corpus. Using our estimates, we're going to try and predict the probability of words in the context, as we talked about last time. So that gives us an objective function from which we can then look at our errors, look at our gradient, and update the vectors so that they learn to predict surrounding words better. And so the incredible thing is that we can do no more than that, and we end up learning word vectors, which actually capture quite a lot of the semantics, the meaning and relationships between different words. So, when this was first discovered for these algorithms, I mean, it really feels like magic that you can just sort of do this math, simple math over a lot of text, and actually learn about the meanings of words, that it's sort of surprising that something so simple could work. But as time has gone on, this same recipe has then been for all kinds of learning about the behavior of language from neural networks. So let's just go through a sense of how that is. But before we do that, let me just mention, so for our word-to-vec algorithms, the only parameters of the model are these word vectors. They're the outside word vectors and the center word vectors, which we actually treat as disjoint, as I mentioned last time. And when we do the computations, we're considering the dot product between the various possible outside words with our center word, and we're using those to get a probability distribution over how likely the model thinks that different outside words were. And then we're comparing that to the actual outside word in the context, and that gives us our source of error. So as such, this is what's referred to in NLP as a bag of words model, that it doesn't actually know about the structure of sentences or even what's to the left and what's to the right. It's predicting exactly the same probabilities at each position to the left or right, but it's wanting to know about what kind of words appear in the context of the center word. So I just wanted to stop this for a minute and let's see, not that one. Just give you some kind of a sense that this really does work. So this is a little Jupyter notebook that I've got for this. Okay, and so this is using, and here I'm using a package GenSim, which we don't continue to use after that really, but it's sort of one package that lets you load and play with word vectors. And the word vectors I'm going to use here are glove word vectors. And actually I'm going to glove was a model we built at Stanford, and I'm going to actually talk about it a little bit later. So strictly speaking, these aren't exactly word vectors, but they behave in exactly the same way. And so, okay, so now it's loaded up my word vectors because the word vectors are a big data file. And so as we've discussed, for a word, right, that the representation of any word, here is bread, is just a vector of real numbers, right? So I'm using 100-dimensional word vectors to keep things quicker for my class demo. So this is the word bread. And then I can say, well, what's the representation for croissant? This is croissant. And we can sort of get a visual sense of, oh, they're at least a little bit similar, right? So the first components are both negative. The second components are both positive. The third components are both negative and large. The fourth components are both positive, right? They seem like they're kind of similar vectors, so that seems kind of hopeful because that means that it knows that bread and croissant are a bit similar to each other. This package has a nice simple function where rather than doing that by hand, you can just ask it about all the word vectors and say which ones are most similar. So I can ask it what words in its vocabulary are most similar to USA. And in this model, everything's been lowercased, I should mention. And so if I do that, it has Canada, America, U.S.A, then United States, Australia. Well, those seem a fairly reasonable list of most similar words, though you might think it's a little strange that Canada wins out over the USA with dots over it. Similarly, I can ask it what's most similar to banana, and I get coconut, mango, bananas, potato, pineapple, fruit, etc. Again, pretty sensible, a little bit of a bias to more tropical fruits. Or I can go to croissant and ask what's most similar to croissant. The most similar things to croissant isn't bread, but it's things like brioche, baguette, focaccia, which sort of basically makes sense, though here's pudding here. And I've got, wait, I'd already done, oh, sorry, yeah, I remember what this is. Right, so with this most similar, you've got a positive word vector, and you're saying what other words are most similar in position to that. There's something else you can do, which you can say is, let me take the negative of that word vector and say, what's most similar to the negative of it? And you could possibly think, oh, that might be useful to find antonyms or something like that. I mean, the truth is it isn't. If you ask for the things that are most similar to the negative of the banana vector, and in most other vectors it's the same, you get out these weirdo things that you're not really sure if they're words at all, or maybe they are in some other language, or some of them are names, right? Like Shunichi's a Japanese name, but not very useful stuff. Don't really feel like a negative of banana. But it turns out that from there we get to this powerful ability of that was observed for word to vec, which is that we could isolate semantic components and then put them together in interesting ways. So looking at this picture, what we could do is start with a positive vector for king, from the origin up to king. Then we could use the negation to say, subtract out the vector for man, and then we could have another positive vector of add on the vector for woman. And then we can ask the model is, if you're over here in the space, what is the nearest word to you over there? And so that's what this next thing does, right? It sort of says, positive vector for king, negative for man, also positive for queen. Where does that get you to? And that gets you to queen. Yay! And so this was the most celebrated property that was discovered with these word vectors, that they weren't only good for meaning similarity, but that they were good for doing these kind of meaning components, and these got referred to as analogies, because you can think of them as A is to B is C is to what. So it's sort of like woman is to king, man is to king, or king is to man as, I'm saying this the wrong way around. Man is to king as woman is to what in the analogies. And so here I've defined a little function that is now saying this little function just automates that and will compute analogies. And so now I can ask it in just this analogy format. Man is to king as woman is to queen. And that one was sort of the canonical example, but you can actually sort of have fun with this. And I mean, this is pretty old-fashioned stuff, I feel like I'm maybe like now at this point an old guy talking about how much fun we used to have sitting around the radio, listening to radio plays, because basically no one uses this stuff anymore, and there are much, much better and fancier things like ChatGPT. But back in the day when I was younger, it was really stunning already just how this very simple model built on very simple data could just have quite good semantic understanding and do quite good analogies. So you can actually, play with this quite a bit and have a bit of fun. So you can do something like analogy, Australia, beer, France. Okay, what do people think the answer will be? Close. The answer gives us champagne, but that seems a pretty good answer. I could then put in Russia. What do people think? Vodka. Yeah, you can get back vodka. This is actually works kind of interestingly. I could do a different one. I can test something different. I can do something like pencil is to sketching as camera is to photographing. Yeah, that works quite well. we built this model in 2014, so it's a little bit out of date in politics. So, well, we can't do the last decade of politics, which is maybe fortunate. But, we could try out older politics questions. So we could try Obama is to Clinton as Reagan is to, if you remember your US world history class, any guesses what it's going to say? There's a Bush one. Any other ideas? Some people have different opinions of Bill Clinton. Any?
Nixon.
What it answers is Nixon, which I think is actually kind of fair. You could also get it to do some just sort of language syntactic facts. So you can do something like tallest to tallest as long is to. This one's easy. So, with this simple method of learning, with this simple bag of words model, it's enough to learn a lot about the semantics of words and, stuff that's beyond conventional semantics, right? Like our examples with Australia as to beer, as Russia as to vodka. I mean, that's sort of cultural world knowledge, which goes a little bit beyond what people normally think of as sort of word meaning semantics, but it's also in there. Yes?
Perhaps subtract the distance from, let's say, like man and king, does that also capture a concept of relationship between two words? Like, would that give you back like ruler or like something like that? Where we're taking the distance, like the difference between two vectors does capture some concept.
The distance between man, so man compared to king should be a ruler concept, but isn't that what I'm using? Because then I'm taking the distance between man and king is what I'm adding on to woman to get to queen, right?
Yeah, so it should capture some concept.
Right, yeah. So I can, depending on if you think of these words, depending on which thing you think of as the analogy, you can think of it, you've both got a vector, a difference vector between words that gives you a gender analogy and one that gives you a ruler analogy. Yeah, absolutely. Any other questions? Yeah?
In the watch algorithm, we get two vectors, like for each word, a U and a V, but here you only have one vector. So how do you go from two to one?
Yeah, good question. I mean, the commonest way in practice was you just average the two of them. And really you sort of find out that they end up very close, because if you think of it, since you're going along every position of the text, you're both going to be the case where if the text is sort of, the octopus has legs, you're going to have octopus in the center with legs in the context, then a couple of time steps later it's going to be legs in the center with octopus in the context. So, although they vary a bit for all the regions of the neural nets vary, basically they end up very similar and people normally just average them. Yeah.
So use this, the answer of one to then be placed into the analogy function of the other and see how far away you can go before it starts to break down?
I think you can. So you're wanting to...
How far away, how distant of a relation between two words can you do before it starts providing incorrect relationships between words?
Are you wanting to sort of make 2 steps from somewhere, or?
Yeah, like 2 steps or 3 steps, or like how many steps can you go away from king before it starts failing this kind of?
So it doesn't always work. I mean, there are certainly examples that have failed. I'm sort of shy to try that now because I don't have a predefined function that did it, and that might take me too long. But you could play with it at home and see how it works for you. Okay.
Curious, Well, okay, as a clarification, why is it that we use two separate sets of vectors for word2vec? Is it just to get more parameters, or is there?
I'll get back to that. Maybe I should go on at this point. Let me move on and kind of just get through some more details of the word2vec algorithm. Just a technical point on this class so you don't make any big mistakes and waste your weekend. I mean, for most instances of 224N, we've actually had people implement from scratch word2vec as assignment 2. But, you know, for this quarter, doing it in spring quarter, as you probably know, spring quarter is actually a little shorter than the other 2 quarters. We decided to skip having people implement word2vec. So don't look at the old assignment 2 that says implement word2vec, or else you'll be misspending your time. Wait for the newer assignment 2 to come out. But, you know, despite that, let me just sort of say a little bit more about some of the details. Right, yeah, so why 2 vectors? So the 2 vectors is it just makes the math a little bit easy. So if you think about the math, right, if you have the same vectors for the center word and for the outside words, well, for whatever the center word is, let's say it's octopus, that when you're going through the trying out every possible context word for the normalization, at some point you'll hit octopus again. And so at that point, you'll have a quadratic term, right? You'll have the x squared of the octopus vector. And that kind of messes up, I mean, you're clever people, you could work out the math of it, but it makes the math more of a mess, right? Because every other term it's something different, and it's just like ax, and then at one position you've got an x squared. So it just makes the math messier, and so they kept it really simple by just having them be disjoint vectors. But it doesn't make it better. I mean, it actually turns out it works a fraction better if you do it right. But in practice, people have usually just estimated them separately and then averaged them at the end. If you actually look at the paper, here's Mikolov et al., you can find it, 2013 paper. There's actually sort of a family of methods that they describe. So they describe 2 methods, one of which was that you have an inside word that's predicting the words around it, and then the other one tried to predict the center word from all the words in the context, which was called continuous bag of words in their paper. The one that I've described as skipgram, which is simpler and works just great. But then the other part of it is for working out what loss function to be used for training. And what I've presented so far is naive softmax, where we just consider every possible choice of a context word and just run all the math. You know, that's totally doable, and with our modern super fast computers, it's not even that unreasonable to do. We do things like this all the time. But at least at the time that they wrote their paper, this seemed kind of expensive, and they considered other alternatives like a hierarchical softmax, which I'm not going to explain right now, but I do just want to explain negative sampling. Okay, so this is just to sort of see a bit of a different way of doing things. So for what we did last time, we had this sort of straightforward softmax equation. And so in the denominator, you're summing over every word in the vocabulary. And so if you might have 400,000 words in your vocabulary, a lot of words in human languages, you know, that's kind of a big sum, especially when for each element of the sum, you're taking a dot product between 100-dimensional or 300-dimensional vectors and then exponentiating it, right? A lot of math going on somewhere in there. Maybe we could short circuit that. And so the idea of the negative sampling was to say, well, rather than evaluating it for every single possible word, maybe we could just sort of train some simpler logistic regressions where they're going to say, you should like the true word that's in the context, and if we randomly pick a few other words, you shouldn't like them very much. and that's skip-gram negative sampling. So that's what this looks like as an equation. So we've got our center word and our actual context word, and we're saying, well, let's work out the term for the actual center word. We'd like this to be high probability, so since we're minimizing, we're going to negate that and have it go down. And then we're going to sample some other words, and we'd like this to be the opposite. But the other thing that we've changed here is now we're not using the softmax anymore. We're using this sigma, which stands for the logistic function, which is often called the sigmoid. Sigmoid just means S-shaped, but you know, you can actually have an infinity of S-shaped functions, and the one that we actually use is the logistic function. So the logistic function has this form and maps from any real number to a probability between 0 and 1. So what we're wanting to say at that point is, for the real outside word, we're hoping that this dot product is large, so its probability is near 1, and so that will then sort of help with the minimization. And for the other words, we'd like their probability to be small, so we'd like them to appear sort of over here. And that's what this is calculating. But as written, it's sort of sticking the minus sign on the inside there, which works because of this is symmetric, right? So you're wanting to be over here, which means that if you negate it, you'll be on this side, which will be large. Okay. And so then the final bit of this, which is the asterisk, is so we're going to pick a few words, you know, it might only be 5 or 10 that are our negative samples, but for picking those words, what works well is not just to sort of pick sort of randomly, uniformly from all the 400,000 words in our vocab. What you basically want to do is sort of be paying attention to how common the words are. So something like that is a really common word. And so we refer to that as the unigram distribution. That means you're sort of just taking individual words independently, how commonly they are. So about 10% of the time you'd be choosing the. So that's sort of roughly what you want to do for sampling, but people have found that you can actually do even a bit better than that. So the standard thing that they presented for word2vec is you're taking the unigram probability of the word and raising it to the power 3/4. What does that end up doing? Question for the audience. If I take probabilities and raise them to the 3/4.
Some less frequent words just become sampling more.
Correct. Yeah, so raising it to the 3/4 means that you're sort of somewhat upping the probability of the less frequent words. So you're sort of in between, you know, between having every word uniform and exactly using their relative frequencies in the text, you're sort of moving a little bit in the direction of uniform. And so you get better results by going somewhat in the distance of sampling more uniformly, but you don't want to go all the way there, which should correspond to, I guess, putting a 0 in there rather than a 3/4. Okay. Yeah. Okay, let's see, I had an aside here, but time rushes along, so let's not bother with the aside. It's not that important. Okay, so that's the word2vec algorithm that we've seen all of in its different forms. A reasonable wonder that you could have at this point is, you know, this seems a kind of a weird way of doing what we're wanting to do, right? The idea is, look, we have this text, we have words, and we have words in the context of words. It sort of seems like an obvious thing to do would be to say, let's just count some statistics. We have words, and there are other words that occur in their context. So let's just see how often the word swim occurs next to octopus and how often the word fish occurs next to octopus. Let's get some counts and see how often words occur in the context of other words. And maybe we could use that to calculate some form of word vectors. And so that's something that people have already also considered. So if we use the same kind of idea of a context window, we could just make a matrix of how often words occur in the context of other words. And so, here's a baby example. My corpus is, I like deep learning, I like NLP, I enjoy flying. And my context window I'm using is just one word to the left and the right. And then I can make this kind of co-occurrence count matrix where I'm putting in the counts of different words in every context. And because my corpus is so small, everything in the matrix is a 0 or 1, except for right here where I've got the 2's because I have I like twice, right? But in principle, I've got a matrix of counts for all the different counts here. So maybe, this gives me a word vector, right? Here's a word vector for deep, is this long vector here. And, I could just say that is my word vector. And indeed, sometimes people have done that, but they're kind of ungainly word vectors because if we have 400,000 words in our vocabulary, the size of this matrix is 400,000 by 400,000, which is a lot worse than our word vectors, because if we're making them only 100-dimensional, we've only got 400,000 by 100, which is still a big number, but it's a lot smaller than 400,000 times 400,000. So that's inconvenient. So when people have started with these kind of co-occurrence matrix, the general thing that people have done is to say, well, somehow we want to reduce the dimensionality of that matrix so that we have a smaller matrix to deal with. And so then how can we reduce the dimensionality of the matrix? And at this point, if you remember your linear algebra and stuff like that, you should be thinking of things like PCA, and in particular, if you want it to work for any matrix of any shape, there's the singular value decomposition. So there's a classic singular value decomposition for any matrix. You can rewrite it as a product of 3 matrices, a U and a V, which are both orthonormal, which means that you get these independent vectors that are orthogonal to each other. And then in the middle, we have the singular vectors, which are ordered in size. This is the most important singular vector, and these are sort of weighting terms on the different number of the different dimensions. And so this is sort of the full SVD decomposition, but part of it is irrelevant because if I've got this picture, nothing is happening in the part that's sort of shown in yellow there. But if you want, at the moment, this is just a full decomposition. But if we're wanting to have sort of smaller, low-dimensional vectors, well, the next trick we pull is we say, well, we know where the smallest singular vectors are, so we could just set them to 0. And if we did that, then more of this goes away, and we end up with 2-dimensional representations of our words. And so that gives us another way of forming low-dimensional word representations. And this had actually been explored before modern neural word vectors using algorithms such as latent semantic analysis. And it has sort of half worked, but it never worked very well. But some people, especially in psychology, had kept on working on it. And among other people, in the early 2000s, there was this grad student, Doug Rohde, who kept on working on it. And he came up with an algorithm that he called Coles. And, he'd known, as other people before him had known, that just sort of doing an SVD on raw counts didn't seem to give you word vectors that worked very well. But he had some ideas to do better than that. So one thing that helps a lot is if you log the frequencies. So you can put log frequencies in the cells. But then he sort of used some other ideas, some of which were also picked up in Word2Vec, one of which is ramping the windows so that you count closer words more than further away words. He used Pearson correlations instead of counts, etc. But he ended up coming up with a low-dimensional version of word vectors that are sort of ultimately still based on an SVD. And he got out these word vectors. And interestingly, sort of no one really noticed at the time, but Doug Rohde in his dissertation effectively discovered this same property of having linear semantic components. So look, here we go. Here's so this is actually, a picture from his dissertation. And look here, we've got this meaning component, which is doer of an event. And he's essentially shown with the way he's processed his word vectors that the doer of an event is a linear meaning component that you can use to move between a verb and the doer of the verb. Kind of cool, but he didn't become famous because no one was paying attention to what he had come up with. So once Word2Vec became popular, that was something that I was kind of interested in. And so working together with a postdoc, Jeffrey Pennington, we thought that, there was interest in this sort of space of doing things with matrices of counts, and how do you then get them to work well as word vectors in the same way that Word2Vec worked well as word vectors. And so that's what led into the glove algorithm that was what I was actually showing you. And so what we wanted was to say, look, we want a model in which linear components, sort of adding or subtracting a vector in a vector space, correspond to a meaning difference. How can we do that? And Jeffrey did good thinking and math and thought about that for a bit. And his solution was to say, well, if we think of that ratios of co-occurrence probabilities can encode meaning components. So if we can make a ratio of co-occurrence probabilities into something linear in the vector space, we'll get the kind of result that Word2Vec or Doug Rohde got. So what does that mean? Well, so if you start thinking of words occurring in the context of ice, you might think that sort of solid and water are likely to occur near ice, and gas or a random word like random aren't likely to occur near ice. And similarly for steam, you'd expect that gas and water are likely to occur near steam, but probably not solid or random. And well, if you're just looking at one of these, you don't really get meaning components because you get something that's large here or large here. But if you then look at the ratio of two of these co-occurrence probabilities, then what you get out is that for solid it's going to be large and small is going to be, and for gas it's going to be small. And so you're getting a direction in the space which will correspond to the solid, liquid, gas dimension of physics. Whereas for the other words, it'll be about 1. This is just the wave your hands. This was the conception of the idea. But if you actually do the counts, this actually works out. So using real data, this is what you get for co-occurrence. And indeed, you kind of get these sort of factors of 10 in both of these directions of these two. And the numbers are over there are approximately 1. Jeffrey's idea was, well, we're going to start with a co-occurrence count matrix, and we want to make this turn into a linear component. And well, how do you do that? Well, first of all, it sort of makes sense immediately that you should be putting a log in, right? Because once you put a log in, this ratio will be being turned into something that's subtracted. And so simply all you have to do is have a log bilinear model where the dot product of two word vectors models this conditional probability, and then the difference between two vectors will be corresponding to this log of the ratio of their co-occurrence probabilities. So that was basically the glove model. So you're wanting to, model this dot product such that it's being close to the log of the co-occurrence probability, but you sort of do a little bit of extra work to have some bias terms and some frequency thresholds, which aren't very important, so I'm going to skip past them. But I think that basic intuition as to what's the important thing to get linear meaning components is a good one to know about. Okay, is everyone good to there? Cool. Yes.
Oh, I noticed the original X matrix you showed was like 3 by 5 or something. Shouldn't it be square?
So, yeah, I mean, if you're doing, sorry, yeah, I maybe should have just shown you a square one. If you're just doing vocabulary to vocabulary, yes, it should be square. But there was a bit in the slides that I didn't mention, that there was another way you could do it where you did it words versus documents, and then it would be non-square. But yeah, you're right. So we can just consider the square case. Okay, so, hey, I showed you that demo of the glove vectors, and they worked great, didn't they? So, these are good vectors. But in general in NLP, we'd like to have things that we can evaluate and know whether things are really good. And so everywhere through the course, we're going to want to evaluate things and work out how good they are and what's better and what's worse. And so one of the fundamental notions of evaluation that will come up again and again is intrinsic and extrinsic evaluations. So an intrinsic evaluation is where you are doing a very specific internal subtask and you just try and score whether it's good or bad. So normally intrinsic evaluations are fast to compute, help you understand the component you're building, but they are sort of distant from your downstream task, and improving the numbers internally may or may not help you. And that's the contrast with an extrinsic evaluation, which is that you've got some real task, you want to do question answering or document summarization or machine translation, and you want to know whether some clever bit of internal modeling will help you on that task. So then you have to sort of run an entire system and work out downstream accuracies and find out whether it actually helps you at the end of the day. But that often means it's kind of, indirect, so harder to see exactly what's happening in your task. So for something like word vectors, if we just sort of measure, are they modeling word similarity well, that's an intrinsic evaluation. But, we'd probably like to know whether they model word similarity well for some downstream task, which might be doing web search, right? We'd like, when you say, cell phone or mobile phone, that it comes out at about the same. So that would then be web search might be our extrinsic evaluation. Okay, so for word vectors, two intrinsic evaluations are the ones we've already seen. So there's the word vector analogies. I cheated. When I showed you the glove demo, I only showed you ones that work. But if you play for it yourself, you can find some that don't work. So what we can do is sort of have a set of word analogies and find out which ones work. Now, in general, glove does work. Here's a set of word vectors showing you the sort of male-female distinction. It's kind of good and linear, but in general for different ones it's going to work and it's not work, and you're going to be able to score what percentage of the time it works. Or we can do word similarity. How we do word similarity is we actually use human judgments of similarity. So psychologists ask undergrads and they say, here is the word plane and car. How similar are they on a scale of 1 to 10, or 0 to 10 maybe? Actually, I think it's 0 to 10 here. On a scale of 0 to 10, and the person says, 7. And then they ask another person, and they average what the undergrads say, and they come out with these numbers. So, you know, Tiger gets 10, book and paper got an average of 7.46. Plane and car got 5.77, stock and phone got 1.62, and stock and Jaguar got 0.92. Noisy process, but you roughly get to see how similar people think words are. And so then we ask our models to also score how similar they think words are, and then we get models of how well the scores are correlated between human judgments and our models' judgments. And so here are sort of a big table of numbers that we don't need to go through all of, but you know, it sort of shows that a plain SVD works terribly. Simply doing SVD over log counts already starts to work reasonably. And then, you know, here's the two word-to-vec algorithms, Siebel and skipgram, and here are numbers from our glove vectors. And so you get these kind of scores that you can then score different models as to how good they are. And well, then you can also, that's the only thing I have there. But you know, what can you do for downstream evaluation? Well, then you want to pick some downstream task. And so a simple downstream task that's been used a lot in NLP is what's called named entity recognition. And so that's recognizing names of things and what type they are. So if the sentence is Chris Manning lives in Palo Alto, you want to say Chris and Manning, that's the name of a person, and Palo and Alto, that's the name of a place. So that can be the task, and well, that's the kind of task which you might think word vectors would help you with. And it's indeed the case, right? So here, what's labeled as discrete was a baseline, symbolic, probabilistic, named entity recognition task, and by putting word vectors into it, you can make the numbers go up. So these numbers for glove are higher than the ones on the first line, and so I'm getting substantial improvements from adding word vectors to my system. Yay. Okay. I'll pile ahead into the next thing. This next one I think is interesting and we should spend a minute on, and it came up in your questions last time. Words have lots of meanings. Most words have a whole bunch of meanings. Words that don't have a lot of different meanings are only some very specialized scientific words. Okay, so my example of a word with multiple meanings is probably not the first one you think of all the time. The most famous example of a word with a lot of meanings is bank, which already came up last time, and I use star, which is another one. Here's a word that you probably don't use that often, but it still has lots of meanings. So the word pike, what are some things that the word pike can mean? A fish, yes, it's a kind of fish. Okay, we've got one. What else can a pike be? Yeah.
A spear?
A spear, yeah, for the Dungeons and Dragons crowd. Yeah, there's a long arm, right? Yep, that's another one. Yeah. A road, right? Yeah. So pike is used as a shorthand for a turnpike. But why it's called a turnpike was, originally you had, the speary-looking thing at the start of it as sort of count people. Okay, we've got three other meanings for pike. Yeah.
Is it also a frat? Like a fraternity? The name of a fraternity?
I'll believe you. I can't say I know that one. Other pikes?
Something sharp as like a needle. Something sharp.
Maybe. I mean, I think it's really the sort of pike as the weapon. Any other scratch your head? One that I think a lot of you will have seen in diving and swimming. You can do a pike. Olympics, if you see Olympic diving, there are pikes. Anyone seen those? Trust me, there's a pike. Okay, and so we've sort of been doing the noun uses, but you can also use pike as a verb, right? Like once you've got your medieval weapon, you can pike somebody, and that's a usage of pike. And you can do other ones, right? So here we go. Here's ones I got from a dictionary. We got most of those. There are sort of weirder usages, right? Like coming down the pike, that's kind of a metaphorical use that comes from the road sense, but it sort of ends up meaning the future. In Australia, we also use pike to mean sort of chicken out of doing something. But I don't think that usage is really used in the US. Anyway, words have lots of meanings. So how can you deal with that? Well, one way you could deal with it is to say, okay, words have several meanings, and so we're just going to say words have several meanings, and then we're going to take instances of words in text. We're going to cluster them based on their similarity of occurrence to decide which sense of the word to regard each token as, and then we're going to learn word vectors for those token clusters, which are our senses. And you can do that. We did it in 2012, before Word2Vec came out. So you see here we have bank 1, and somewhere over here we have bank 2, and here we have Jaguar 1, Jaguar 2, Jaguar 3, Jaguar 4. And this really works out great, right? So Jaguar 1 picks out the sense of the kind of car, right? And it's close to luxury and convertible. Jaguar 2 comes right close to software and Microsoft. And this one's a bit of an historical one, but that's when most of you were 5 or whatever. You might remember Apple used to use large cats for versions of Mac OS, right? So sort of Mac OS 10.3 or something like that. A long time ago it was called Jaguar, right? So it's software close to Microsoft. Jaguar 3, okay, string keyboard, solo, musical, drum, bass. That's because there's a Jaguar keyboard. And then finally, the sort of what we think of as the basic sense, but turns up rather less in text corpora normally. Jaguar next to hunter is the animal, right? So it's done a good job at learning the different senses. But that's not what's actually usually done these days. And instead, what's usually done is you do only have one vector for Jaguar. And when you do that, or pike here, the one vector you learn is a weighted average of the vectors that you would have learnt for the senses. It's often referred to as a superposition because somehow neural net math people like to use physics terms. And so they call it a superposition, but it's a weighted average. So you're taking the relative frequency of the different senses and multiplying the vectors you would have learned if you'd had sense vectors, and that's what you get as the representation as a whole. I can make a sort of a linguistic argument as to why you might want to do that, which is, although this model of words have senses is, very long-standing and common. I mean, it's essentially the way dictionaries are built, right? You look up a word in the dictionary and it says sense 1, sense 2, sense 3, and you get them for things like bank or Jaguar as we're talking about. I mean, it's sort of really a broken model, right? That word meanings have a lot of nuance. They're used in a lot of different contexts. There are extreme examples like bank, wherever it was, where we have finance bank and bank of a riverbank over here, where it seems like the senses are this far apart. But you know, most words have sort of different meanings, but they're not actually that far apart, and trying to cut them into senses seems actually very artificial. And you know, if you look up 5 different dictionaries and you say how many senses does this word have, pretty much everyone will give you a different answer. So the kind of situation you have is a word like field. Well, a field can be used for a place where you grow a crop. It can be used for sort of natural things like a rock field or an ice field. It can be used for a sporting field. There's the mathematical sense of field. Now, all of these things sort of have something to do with each other. I mean, the math one's further away, but the physical ones are sort of flat spaces. But you know, the sense of it being a sporting field is clearly kind of different from the sense of it being an ice field. Is the ice field and the rock field different, or am I just modifying them? Are they different senses? Right, so really you sort of have a kind of what a math person would say is sort of like some probability density distribution over things that can be meant by the meaning of a word. So it sort of maybe makes sense to more use this model where you're just actually saying we have a vector that's an average of all the contexts. And we'll see more of that when we get to contextual word vectors later on. But one more surprising result on this is since you have the vector for pike overall being the sum of these different sense vectors, you know, standard math would tell you that if you just have the single vector, there's no way that you can recover the individual sense vectors. But higher math tells you that actually these vector spaces are so high dimensional and sparse that you can use ideas from sparse coding theory to reconstruct the sense vectors out of the whole vector. And if you actually want to understand this, some of the people in statistics, David Donahoe I think is one of them, teach courses on sparse coding theory. I'm not going to try and teach that, but you know, here's an example from this paper, the Sanjeev Arora et al., where one of the et al.'s is Tung-Yu Ma, who's now faculty in computer science here, where they are starting off with the word vector and using sparse coding to divide out sense vectors from one word vector, and they work pretty well, right? So here's one sense of tie, which is piece of clothing, another sense of tie, which is ties in a game. This one is sort of similar to that one, and I'll admit, but this sense of tie here is then a tie as sort of you put on your electrical cables. Then you have the musical sense of tie, right? At least 4 out of 5. They've done a pretty good job of getting senses out of this single word vector by sparse coding. So sparse coding must be cool if you want to go off and learn more about it. Okay. Okay, so that's everything I was going to say about words, vectors, and word senses. Is everyone good to there? Any questions? I'll rush ahead for the last 2 pieces. Okay, so I just wanted to start to introduce in the last 15 minutes the ideas of how we can build neural classifiers and how we start to build in general neural networks. I mean, in a sense, we've already built a very simple neural classifier because our word-to-vec model is predicting what words are likely to occur in the context of another word. And you can think of that as a classifier. But let's look at a simple classifier like our named entity recognizer that I mentioned before. So for the named entity recognizer, we want to label words with their class. So we want to say these two words are a person, but the same words, Paris and Hilton, are then locations in this second sentence. So words can be ambiguous as to what their class is. And the other state is that they're not a named entity at all. They're just a word that is some other word. And this is something that's used in lots of places as a bit of understanding. So if you've seen any of those web pages where they've sort of, tagged company names with a stock ticker, or there's links on a Wikipedia page to a Wikipedia page or something like that, right? You've got named entities where commonly after finding the named entities, you're doing this second stage of entity linking, where you're then linking the named entity to some canonical form of it, like a Wikipedia page. But we're not going to talk about the second part of it for the rest of the day. And so we could say that building with our word vectors, we've got this simple task where what we're going to do is we're going to look at a word in context, because sometimes Paris is a name of a person, sometimes it's a location. And so we're going to want to look at this word in its context and say, aha, this is a name of a location in this instance. And so the way that we're going to do it is we're going to form a window classifier. So we're going to take a word with a couple of words of context on each side, and for the words in our context window, we're going to use our word vectors because we want to show they're useful for something. And then we want to feed this into something that is a classifier. And our classifier, it's actually going to be a really simple classifier. We're only here going to do location or not a location. So this one here, we're wanting to say for this window here, yes, it's a location. And whereas if it had been, I love Paris Hilton greatly, then we'd be saying no, because Paris, the word in the middle of the context, then isn't a location. So that's sort of the idea of a classification or classifier. We're assigning some set of classes to things, right? So in general, for classifiers, we do supervised learning, which means we have some labeled examples, our training data set. So we have input items xi, and for each one we've got a class yi. So I had for my training examples ones like, I love Paris Hilton greatly. That was negative, not a location. And I visit Paris every spring. That's positive, that is a location, where I'm actually classifying the middle word. Okay, so inputs, labels, and in general we've got labels are a set of classes. So my set here is simply location, not a location, but I could get fancier and I could say I've got 5 classes. I've got location, person, name, whatever other ones there are, company name, drug name, right? I could be assigning a bunch of, or other, not a name, a bunch of different classes. But I'm going to be doing it with only 2 because I'm using this example on next Tuesday's lecture as well, and I'm wanting to keep it simple. So that's what we're going to do. And so what we're going to be using in our class is neural classifiers. And so I just wanted to sort of go through quickly just the sort of food for thought as we go into it. So for a typical stats machine learning classifier, you can build classifiers like logistic regression or softmax classifiers, or other ones like support vector machines or naive Bayes or whatever else you might have seen. The vast majority of these classifiers are linear classifiers, meaning that they have a linear decision boundary. And when we're learning these classifiers, we're learning parameters here, W, but our inputs are fixed, that our inputs are represented by symbols like or quantities. So we have fixed inputs. We learn parameters as weights that are used to multiply the inputs, and then we use a linear decision boundary. So when we have our neural classifier, we're kind of getting some more power. So first of all, we're not only learning weights W for our classifier, we're also learning distributed representations for our words. So our words can sort of re-represent, our word vectors re-represent the actual words as symbols and can move them around in the space. So that in terms of the original space, we've got a non-linear classifier that can represent much more complex functions, but we will then sort of use the word vectors to re-represent those words to do a final classification. So at the end of our deep network, which we're about to build, we will have a linear classifier in terms of our re-represented vectors, but not in terms of our original space. Let me try and be concrete about that. Okay, so here's what I'm going to use, and we'll use again next Tuesday as my little neural network. And so I start with some words. Museums in Paris are amazing. I first of all come up with the word embedding of those using my word vectors. So now I've got this sort of high dimensional vector, which is just a concatenation of 5 word vectors. So, you know, if I have 100-dimensional word vectors, this is 500-dimensional. And then I'm going to put it through a neural network layer, which is simply multiplying that vector by a matrix and adding on a bias vector. And then I'm going to put it through some nonlinearity, which might be, for example, the logistic function that we've already seen. So that'll give me a new representation. And in particular, if the W is, say, 8 by 500, I'll be reducing it to a much, 8 by 500, I'll be reducing it to a much smaller vector. Right, so then I can do after that, I can multiply my hidden representation in the middle of my neural network by another vector, and that will give me a score, and I'm going to put the score into the logistic function that we saw earlier to say what's the probability, this is the location. So at this point, my classifier is going to be a linear classifier in terms of this internal representation that's used right at the end, but it's going to be a nonlinear classifier in terms of my word vectors. Okay. Great. Here's one other thing. This is just sort of a note for learn ahead, since you want to know this when we start doing the next assignments. I mean, up until now, I've presented everything as, you know, doing log likelihood and negative log likelihood for building our models. Very soon now, assignment 2, we're going to be starting to do things with PyTorch. And when you start working out your losses with PyTorch, what you're going to be wanting to use is cross-entropy loss. And so just let me quickly say what cross-entropy loss is. So cross-entropy is from information theory. So if you have a true probability distribution P and you're computing a probability distribution Q, your cross-entropy loss is like this. So it's the log of your model probability, the expectation of that under your true probability distribution. But there's sort of a special case, whereas if you have ground truth or gold or target data where things are labeled 1, 0, so like for examples of I love Paris, when warm, right? I'm just labeling it 1 for location, probability 1 it's the location, probability 0 it's not a location. So if you're just labeling the right class as probability 1, then in this summation, every other term goes to 0, and the only thing you're left with is what probability is my model, what log probability is my model giving to the right class. And so that then is your log likelihood, which we can use for the negative log likelihood. A little bit of a complication here. Just remember that you'll want to use cross-entropy loss in PyTorch when building the model. Okay, before we end today, here is my obligatory one picture of human neurons. Don't miss it, because I'm not going to show any more of these. Okay, these are human neurons, right? Human neurons were the inspiration for neural networks, right? So human neurons have a single output which comes down this axon, and then when you have these outputs, they then feed into other neurons. I guess I don't really have an example here, but in general, one output can feed into multiple different neurons. You can see the different things hanging into it. So, you know, you have the output connecting to the input, and sort of where you make this connection, right, that's the synapses that people talk about. And so one neuron will normally have many, many inputs where it picks things up from other neurons, and they all go into the nucleus of the cell, and the nucleus combines together all those inputs. And kind of what happens is, if there's enough positive activation from all of these inputs, it then sends signals down as output. Now, strictly how neurons work is that they send spikes. So the level of activation as a neuron is its rate of spiking. But that immediately got turned in artificial neural networks into just a real value as to what is its level of activation. And so it does this. So this was kind of the genuine inspiration of all of our neural networks, right? So a binary logistic regression is kind of a bit similar to a neuron, right? It has multiple inputs. You're working out your total level of excitation, where in particular you can have inputs that are both exciting, positive inputs, and inputs that are negative, which are then inhibitory inputs. You combine them all together and you get an output that's your level of excitation, and you're then sort of converting that through some nonlinearity. And so this was proposed as a very simple model of human neurons. Now, human neurons are way more complex than this. And some people, like neuroscientists, think we maybe should be doing a better model of actual human neurons. But in terms of what's being done in the current neural networks eat the world revolution, everyone's forgotten about that and is just sticking with this very, very simple model, which conveniently turns into linear algebra in a very simple way. So this gives us sort of like a single neuron, but then precise, right? So this is, single neuron, if you use the logistic function, is identical to logistic regression, which you've probably seen in some stats class or something. But the difference is that for neural networks, we don't just have one logistic regression, we have a bunch of logistic regressions at once. And well, that'd be tricky if we had to define what each of these logistic regressions was calculating. But what we do is we just feed them into another logistic regression. And so we have some eventual output that we want to be something, like we want it to say, you know, this is or isn't a location. But then what will happen is by our machine learning, these intermediate logistic regressions will figure out all by themselves something useful to do. That's the magic, right? So that you get this sort of self-learning property where the model has a lot of parameters and internally will work out useful things to do. So in general, we can get more magic by having more layers in the neural network, and that we will build up functions. So effectively, these intermediate layers let us learn a model that re-represents the input data in ways that will make it easier to classify or easier to interpret and do things with downstream in our neural network. And it's time, so I should stop there. Thank you.